Okay, we're doing a video now on specialist maths, stage 2, proof using vectors. So we just have a few questions based on some of the skills that we've done so far. Okay, so let's have a look at some of these questions. So in these questions, we're using skills to determine proofs about things like perpendicularity. So think about the dot product, parallelism. Think about length of A dot B equals A length of A times length of B. And we'll find some other ones as well. So let's go through these. All right, start off with question 1. A and B are the position vectors of two distinct points, A and B, another which is the origin. Show that A plus B equals A minus B, then A is perpendicular to B using a vector algebraic method or a geometric method. Let's draw that. All right, so I'm just going to pick a point O, and we'll just draw out a point that represents A. That's the position vector of A. We just call that A. All right, and then somewhere down here, we just draw out B. Okay, that is the position vector of B. All right, now, if I was to a little more precise. Let's make it on that point there. Okay, so the addition of A plus B, well, A, I'm going to add B. So I'm actually going, okay, what have I done? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Right. So from here, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's over there. All right. So that is, if I was to draw that up, I can just pull that point C for the purposes of this exercise. And if I was to draw a vector going from the start of O to the end of C, that could also be written as A. So what I did was I graphed B on there, so A plus B. It's going across there. And if these are OB is parallel OC, what I've drawn here is a parallelogram. So I just join up these points as well. And I've just O, A, B, C is a parallelogram. All right, just something to help. Okay, now the other one I did was B, A minus B. Okay, so A minus B, we're going up that way. Okay. All right, so we got A minus B up that way. So let's write that down, OC. OC equals A plus B and BA. Oops. Equals A minus B. All right. So the idea the lengths of these two have to be equal. So use the vector algebraic argument. All right. So I can consider this. A plus B. Equals. All right, B minus A. Or A minus B. Doesn't really matter. I'm going to go and I'm going to square these. Well, that could be considered the dot product of itself, but itself being two things, a plus b and b minus a. And we can use expansion rules in a moment. Okay, so let's expand that out. A dot a plus b dot a plus a dot b plus b dot b equals a dot a minus a dot b minus the orders of these are interchangeable, so you don't have to be too particular with them for the dot product. And then plus b dot b. Now these are the lengths squared. So a dot a is its length squared, and b dot b is its length squared. But also you notice that these are also on the both sides, so we're going to subtract them out. Move what's across here. A dot b. Bring those across. You have 4 lots of these. Equals 0. And what you've proven here is a dot b equals 0, which implies that a is at right angles to b, which is what you wanted to prove in the first place. Okay. That's the vector method. The geometric method will be, well, the diagonals of OA, BC are equal in length. Implies that OA, BC is a rectangle. And that implies that well, basically OA, the angle A to O to B equals 9 degrees. So those are the two proofs there. All right. So let's move on to question 2. All right, question 2. Okay. All right, consider a quadrilateral ABCD with the midpoints and sides of the blah, 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 blah. Okay, we just have a quadrilateral. Draw it any way, basically. So you got 4 points. But these midpoints need to be where they're meant to be. Midpoints. N, M, P, and Q for ABCD. All right. Prove that M and PQ is a parallelogram. Well, what we have to do is prove that two pairs of opposing sides are equal length. Now, when I did this one before, I found you needed to, because there's nothing special about ABCD. It is actually a general quadrilateral, so you can't assume opposite sides equal length or parallel or anything to that nature. You have to actually come up with 3 vectors for this. So I'm just going to say AM equals actually I'll do AQ equals Q, that makes sense. AM equals S, and I'm going to say BN. Okay, so that should be enough to construct vectors out of. All right, so I need a vector for it. I could do a pair like NP and MQ. All right, so if I went to MQ, or maybe I'll go QM. I have a feeling that will work a bit better. Okay, QM. Oh, it doesn't really matter. So QM, I could go to QA and then go to AM. All right, and that ends up being by the thing we chose minus Q plus S. S minus Q. All right, so let's go find the opposite side of that. So P to N. All right, P to N. No, actually, when I did this, no, actually, I needed to work out the fourth side actually to do that. So I'm going to do D to P. Actually, if I'm doing N, PN, P to N, PC, or DP is the same thing as PC, basically. This is the midpoints. I should probably mark those in. I haven't done so far. Yep. DP could be you could travel. Well, one is half of DC, which is half of D to A plus A to B plus B to C, which is one half of minus, so DA is half of Q to A, which is minus Q. Sorry, it's double that. Sorry. So minus 2Q. Okay. Then AP is twice 2M, so that's plus 2S. And BN is twice, sorry, BC is twice BN. So that's 2R. So in other words, is S plus R plus Q. Okay. So that's something that will help us with this. PM. PC plus CN. Okay. PC is the same as DP, which is what I just wrote there. S plus R plus Q. And CN is minus BN, which is BN's R, so minus R. So this ends up being Q. I've actually got the opposite direction. How did that end up happening? Q minus S instead of S minus Q. P to N. I did Q to M. Q to M, Q to A is negative Q. Positive S. And P to N, P to C, P to C, that's correct. CN. Last time I did this, I actually got the order correct. CN. That's minus R. It does cancel out the R, which is what I want. But I got the order of that D to P, D to C, to B. So here's minus Q. How did I get minus Q and I swapped it here? That's my problem. That was minus Q. That's positive S. Yes, I had that the wrong way. S minus Q. So they're the same. Now, once you prove that opposite sides are parallel, then you can also, it comes as a consequence. If you have two vectors with separate coordinate points which are equal, which I just found here, so basically Pn equals Qm, so these are parallel and equal length, then they forms a quadrilateral. It forms a parallelogram. If you don't trust that theorem, basically you can just take any parallelogram, or any quadrilateral such that opposing sides are parallel and equal in length, and you can prove that so are the other side pairs. So that's just, something that I can assume from there, and it's in the notes beforehand, and I proved it before, so I'm going to let it go. All right, so that's question 2. Question 3. Prove that the diagonals of a rhombus bisect the angles of a rhombus using a geometric argument or vector methods. And vector methods is part B. Okay, so I am going to turn this upside down so I'm not wasting pages. Okay. All right, so diagonals of a rhombus. I can make all assumptions that I like about a rhombus. That respect. So all the things that we know about a rhombus is will be holding for the purposes of this. So there's that's not a rhombus, that's a parallelogram. Yeah, close enough. More like a rhombus. So I'm going to call this rhombus O, A, B, C. I'm going to construct everything else around that. I'll call that midpoint now. Yeah, so if it's a rhombus, I can make the assumption that the diagonals bisect each other at right angles. So that might be a useful theorem to use. I haven't actually done this one, or might have, I haven't done it in a while. Okay. Well, the question A says start with a geometric argument. So consider that. All right, well, consider OAC is a triangle is isosceles. All right, then we know that the line and just reference the OA length equals OC. Okay, line that is drawn from the apex to the base, midpoint of base. Cuts, or bisects I should say bisects, the apex angle. So in other words, these two angles are the same. You can repeat that. Repeat for triangle OAB. Oh, yeah, OAB, and you can repeat it on the other side as well. It's the same thing. And so on and so forth. That's the geometric argument. Basically, you can see isosceles triangles inside here, and you can use isosceles theorems. Okay. Okay. So vector methods. All right. So let's have a look at vector methods. All right. So we're going to do okay. So I'll just also note a couple of things. Vector A equals vector C. And AC equals A to C is C take A. OM can be considered A. So it's OA plus AM plus half C take A, which is so I don't think this is elegant, but I kind of know where I'm going with this anyway. Half A plus half C. Okay, so you can come up with a statement for if I was to say, okay, angle AOM I don't think I even need the right angle here. You can use the cosine ways of finding. So cosine theta equals. Okay, I did. I did OM dot OA over okay, and half of that and half of A. Now it really comes down to this. Can I shoot they're the same? Because basically I can switch out the length of A with the length of C because they're the same. So let's have this. I'm just going to draw on the side. What is OM? All right, if I do the dot product of okay, half A plus dot A will end up with half of the length of A plus half C dot A. Now, okay, fair enough. That's one thing. So then that's what I'll get here. Half of the length of A squared plus half C dot A. Now, I don't think this is the most elegant solution, so there might be a better one, but Okay, it is a solution. Now, just repeat this argument for basically finding out COM. And it's the same thing. Cosine theta, and then in that case you have OM dot OC. You end up with the same thing here. Now this is C, but it's the same. They're the same. And what's on top? So I can actually replace that. What's on top will now be. You carry through that. Imagine you dot with C. Well, then you got C dot. They're the same. And then you have 1/2 of A dot C. They're the same. This is all the same. And the denominator is the same. So I've got the A and B. Oh, C, but yeah, it's the same thing. Okay, basically I've shown that C to O to M is equal to A to O to M. And you could basically go through and demonstrate that for all sides. It's kind of a repetitive process because, yeah, you can kind of just you swap out what you call A and C to any position where you have equal lengths, and it's the same argument all the way around the quadrilateral. So if I've shown these pairs are correct, and you can move them around any kind of way you like in that respect. Okay, so that's the vector approach, or a vector approach. I don't know if it's actually the best one. So it's the one I've decided to pick to do. All right, so let's have a look at another one. So actually we're up to question 4. There's not too much left to do. All right. Question 4, construct a triangle OAB with the midpoints of the sides X, Y, and Z. I show it. All right. It's called the medians of the triangle. All right. All right. All right, that's a question 4. So, consider a triangle OA where the midpoints and sides of X and Y are shown. OA, BZ, let O. All right. So just use that diagram shown. All right, draw a triangle. Well, I haven't actually didn't need to draw a Y, but I think they're going that with that. They're meant to meet at a point P. Now they've shown they've put point P in terms of the intersection of Z and X and O and B. So say OX and BZ. But we haven't actually demonstrated the rest of it. But I'm going to draw it nonetheless. Okay, and then that vector is A. And you got OB. Yeah. Okay, right OX. OX and BZ in terms of A and B. Okay, well, AB equals B to A. And you see the midpoint, you've got A and B, and the midpoint between them is basically going to be half A, half B. You can just go and use that because it was kind of stated earlier, but we can just show it again. All right, so X is the midpoint of AB, so we can say A x would be half of that. All right. So let's just do OX equals OA plus AX. Okay, there you go. Demonstrated. All right, so we got that one. But we also have to find, so I might just write that again, OX, that's OX. And we have to find okay, excuse me. All right, we have to go and find BZ. All right, so B to Z. Okay. Can be written as BO plus 1/2 of OA. All right, so minus B plus half A. Half A minus B, if you prefer. Okay. Blah, blah, blah. Okay, OX and BZ intersect at P. Write OP. All right. Suppose OX and BZ opens on intersect at P. Write OP in terms of A and B. Okay. One way to consider this is by traveling. It's not explicitly taught so far, but you can consider it like you're going a scalar multiple of x. So, okay, way to consider is this. All right, now we know that OP. We're going to say OP is some unknown scalar, which is a number less than 1 of OX. Okay. And then we're going to approach it another way. All right, we can go BZ. BZ, BP. Yeah, BP could be considered. Actually, I need to go the same path. Okay, okay, and OP. Let's just take a different path using because I have to find OP, so I have to state things and equate them in terms of OP. I can write them in terms of OX. I'm going to take OP by going OB, and then BP, but that's going to be a. Okay, so that's B, and this is going to be S lots of BZ. Okay, and then I can use those two things. So I've got two statements. I've actually approached OP by two different paths. I have to solve for these things. I'll show you how that works. Okay. TOX. Okay, let's let's write that out. Okay. So OX. So I've got T lots of half A plus half B. Okay. And then OP, this one, I just go up from here. I have okay, and I might just write that on one line. T onto A plus T onto B. I've only got two. I've got S and T, and I've got two vectors to play with, so that should be fun. Okay. BZ. Now BZ was that. Okay, so I've got B plus S lots of minus B okay, BZ or minus B plus 2A. Half 2A, I should say. Oh, hey, what am I doing? Okay, so I could actually summarize that into, okay, I've got 1 take S lots of vector B, and I've got B on 2 lots of A. Now, if I equate the two of these, then I get this statement. T on A plus, yeah, so T on 2A plus T on 2B equals 1S B plus B onto A. Why do I got B onto S? Why do I keep writing S? B. That's not right. I think I'm going to get an inconsistent equation though. Or just something in terms of parameters. It looks like they're the same thing. So S, T equals S in terms of if I equate the B's. It's a bit like kind of complex numbers, like if you have real and imaginary, you have to equate the reals to create the imaginary. All right, so in other words, T onto 1 month S is one equation, or if you prefer, 2 times 2S. All right, and the other one would be T equals S because they're over 2, but if you simplify, it'd be T equals S. Okay, in that case, well then, probably the easiest thing is to solve for S, so I'm going to substitute T in place of here. T equals 2 minus T. Bring that across. They're the same thing anyway. Minus 2. So 3 on T. Equals 2. And T equals 2/3. Yeah. I'll put that in there. You end up with 1/3. Remember that, and S would equal 2/3 as well. All right, so basically OP equals, well, if you want to write in terms of AB, OP is TOX, which is 2/3 from here, and it's also written like that, so it's 2/3 of 1/2 A, half E, which could be considered 2/6 or 1/3. 1/3 of A plus 1/3 of B. That's OP. Okay. Yep. So write YP and PA in terms of A and B. Well, I've got a position vector for P, and I can work out what A those are. Let's have a try at that. Okay. I'm just going to bring that up here and just use this little bit of space. Okay. All right. YP can be Y to O, O plus O to P. Well, that YP okay. y to O is minus 1/2 b plus 1/3 a minus, sorry, plus 1/3 b. Okay, you can express that as 6, 1/3 a. That's not changed. We got 3 on 6 and 2 on 6, so minus 1 on 6b. And all right. All right, what else? Blah, blah, blah. All right, and PA. And P to A. All right, P to A. Let's go to PO. So A. Okay, so then you've got minus 1/3 A plus minus 1/3 B plus A equals, it's 1 full A to go there. So that's 2/3 A minus 1/3 B. Now, the pattern, you might be noticing a pattern here. In terms of those ones, you notice that this is twice of that. Now, you're going to see the pattern a few other places. Okay, we also saw that with OP and OX. Yep. OP. Okay. So OX was half, and that's a third. So it's not quite double though, is it? No, I don't quite notice the same pattern. Sorry, let's get the whole page in there. All right, so actually we don't have any more patterns. We have sure, the medians of the triangle meet at the common point. I thought we just did that. So we just proved that I think you can prove that. Well, we've actually proved that. Okay, so let's just think through to see if we've actually proved part D already. Okay, we've shown that P. Well, actually, yeah, we have. I can see it because P is collinear with with Y and A. And because, all right, now if we do, because YP is equal to, it's basically equal to 2PA. So if you double the A and you double the B, so thereby they are as vectors parallel, but not parallel because they share a common point. So they are collinear. So we've actually proved that. And also, well, P was the intersection of OX and BZ to begin with. So P is a common point of lines OX, BZ, BZ, and YA or AY. Yep, proved. Okay. All right, let's get a bit more space to work. And we only have one more question left to do. Yeah. All right, so question 5. Suppose A and B are non-parallel vectors. A and B are non-parallel vectors. Prove that if K1A, K2B, L1A, L2B, then K1 equals L or L2 equals B. That's kind of actually the rule that I used in question 4, I should say. Well, actually, I did in question 4B. Because I've seen in other courses been taught explicitly. Okay, a non-parallel vector. So we've got vectors. Maybe I'll just have an O just for the purpose of drawing this. Okay, non-parallel vectors, and this could be out any old way. B. Okay. Okay. All right. So if we consider that, okay, we go beyond B. I might even just go a fraction of A. So we just this is the point A, and we'll say that's the point C, and then we'll give that the point B. All right. And we can say, for example, maybe I might even just do this. We'll call that E. Oh, how do I prove this in a general sense? Okay. So let's say OA is A, OB is B. Okay, and I'm going to say that OC is K1. K1A, and OD equals K2B. All right. Especially like you end up, the whole purpose of this sort of rule, it's a very powerful one, question 5, and I used it in question 4, is you can actually prove, you can go by 2 different paths, and you equate these terms and you simplify, and you end up finding out the values. This will actually have a little sneaky peek at the best process of actually proving that to begin with. So maybe we'll have a quick little look-sees. So, all right, let's do it. I'm already to have a quick peek at the other ones, see if there's better methods. Right. All right. Yeah, actually, it's the easy way to prove that is a lot of the rules are congruent triangles, so just repeat. Don't need to repeat the operations if they are the same triangle. Should have picked up that. Yep, that's pretty much what I said here. Okay. Yeah, that's actually how I did it. But the idea you're using what you're proving in 5 to do 4. All right. That's a nice, interesting proof. Okay, so just the proof by contradiction. Fair enough. All right. So let's just have a look at that again. Okay, I see that one. All right, so that's So when you know a type of proof you wouldn't necessarily jump at, just proof by contradiction, but it's okay. Keep it in back of your mind. That's something you might be able to use for something like that. All right. So question 5, proof. Yeah, I'm not going to scrap this one. Scrap the geometric proof kind of setting up. All right. So assume assume that K1 does not equal L1, and so on. K2 does not equal L2. Then, all right, if you did, then equals L1A plus L2B. All right, group these up. So you can subtract that across K2, K1, L1, okay, of A, and you'd have equals K, or actually L2 minus K2 B. All right, now we're going to divide that. So B can be expressed as K1 minus L2 over L2 minus K2. But that implies that is parallel. There's a contradiction, which implies that K1 must equal L1 and K2 must equal L2, unless parallel. Proof of contradiction. Okay, so those are the questions I wanted to go through this video. So I'm going to wrap it up here. Catch you next time.